Alright, today we're going to have a look at another early integrated circuit, or actually a whole family of early integrated circuits. And we've looked at these early DTL diode transistor logic chips before. But today we're going to look at this one here, the FZH101, which is a quad NAND gate. But this one is a little bit special, actually. In addition to 4 NAND gates, it's got an additional input. And the whole family has sort of weird features that we no longer expect in NAND gates. Also, the supply voltages are all over the place. So this whole series is made by a German company, or was made by a German company in, I think, the 70s. And here we've got the data book. It's all in German, but you can get through it quite easily. So these ones, and the one we're looking for here is on the first page. These were made as high reliability integrated circuits for industrial control applications. And somewhere I read the official description is slow gates with enhanced reliability. So let's look at this first page of datasheet here. I said we're going to look at a whole family of them. And here are all the part numbers. And they are different in a couple ways. But we'll look at the internal diagram in a minute, and you can see how they are different. So, first thing, this one here, if you put that into Google Translate, it tells you this is the supply voltage, which is 12 volts, which is quite odd for today. Same D. This is easy, this is high and low. So high is above 7.5 volts and low is below 4.5 volts. It's also a little bit odd for today. Also, you can see these are really quite slow. This is propagation delays, 300 nanoseconds. That's quite a lot into a 10 picofarad load. Right, so let's look at the actual one that we're looking at today. The 101 up here. This is the pinout. As you can see, something odd here that it has. I'll get get one of these plastic pokey hands. But we're back to the paintbrush here. It has one additional input here on the front of the gate next to the output. And you can actually see that in the internal diagram. These are laid out quite simple. It's 3 transistors and 3, 4, 5 diodes. This one being a Zener diode. And a couple of resistors. So as you can see, this input here is distinct from the two regular inputs, the A and B input. Okay, it's a NAND gate. Yeah, that makes sense. If you follow this through, it just looks like a regular NAND gate. But this one here is odd. But it says here, a little 1 next to it. It says down here, only the 111 and the 115 do have that special input, so ours doesn't have that. Although it doesn't tell you what's there instead. I think it's just a don't connect. But yeah, this is odd. I haven't actually read what this is for. I think somewhere later in this document it says you're supposed to put a capacitor here to can only assume so change the propagation delays, or I don't know, slow it down somehow. I'm not sure what this input is for, and I couldn't test it because I don't have the actual chip that has this input. But what I actually know is if you buy this one, the FZH101, it's a sort of do-it-yourself gate, because not only has the weird N input, but it also comes with this N1 input here. And what this is an input where you can connect additional diodes. So if you buy this and you have 4 input NAND gate, but you'd need 7, then you just connect additional diodes to here, and then you have a however many input NAND gate that you need. Yeah, this is quite interesting. You're not used to chips having that anymore, but I think in a way it's quite clever actually doing that. So, and this was a whole series of NAND gates. I think there is, these are different. These are timer chips now. But yeah, this is quite interesting in a way. And you can actually see that the internals here, these are quite similar to the one we looked at before. You could say identical because they are identical. The only thing that changes is the 2-input NAND gate just has 2 diodes here. And interestingly enough, with the 2-input one, they don't give you a pin. But that's because they have fitted 4 in. And you can also see that only 2 of them have this ominous N input. If anybody knows what that N input is for, please tell me. It's got to be something obvious that I'm missing, but it's there for something. Also, this down here is the fan out. So for the high it's 100 and for the low it's 10. And this down here tells you the input will be equivalent to 1 input load. So this is not dragging it down with 5 times what it's supposed to be. Although this is all relative to this specific logic family, I think. So I can only guess what that would be in TTL loads. Probably something completely different. So yeah, this is interesting look into 70s, lesser known 70s logic families. These DTL gates, there are quite a lot of them. I think in one of the future videos we'll have a look at this one here. This one is super interesting. As you can see by how much text it has here in the beginning. This is what it can do. It's a sort of universal timer. If you look at the circuit diagram for this timing chip, you can see this is quite complicated. So they did fairly involved chips, and in a future video we'll have a look at this one. But for today we're doing NAND gate. And as it is tradition for this sort of mini series on integrated circuits, I have put together a little demo. It's just a very easy demonstration as well. So I should probably not the tripod, but I did. But what I should do is I should put the pin out next to the chip here. Let's have a look what is connected here. So we've got our input here, 15 volts in. connected to the input pin, power pin here. We've got ground connected to this pin here. This is these equivalent points here on the diagram. And I've got two ground wires here, one going to the power supply, one going to the signal generator. And then I've got a signal generator running in here. Having it set up for a 9-volt pulse with a DC offset, so it starts at 0 volt. So it's not symmetrical around ground, but it's only positive. It's a positive going pulse. So right what we want. The output here, this is this pin down here, this middle one on here, is connected via a resistor to this LED. And then I've got the input from the signal generator coming in via this lead here. And yeah, there's a resistor stuck to it because yeah, this is a resistor, but it's out of circuit. I just didn't have another piece of wire. So if we turn this on, I'll turn the power supply on first. You can see that this is on, which makes sense because our signal generator input is low. So if it's a NAND gate, we expect this to be high. And yeah, also I bridged the two inputs, these two here. Although I could have just tied one to high and fed the signal into the other one. That would have had the same effect, but I bridged them. So if I turn on signal generator, it's currently set to 1 Hertz. You can see we happily start blinking away with our 70s era DTL logic chip. It was a short little introduction to this family of 6 NAND gates that are all interesting and a little bit different from what we expect a NAND gate to be today. So I hope you liked the video. And now for some, well, channel administration stuff. Today's video was a little short. I'm still working on projects, but I haven't had very much time because I'm still moving. Also, this is probably the last video with the horrible desk with all the holes in it. Because the next one will probably be from new place, so different desk probably. Also, there probably won't be a video Saturday in 2 weeks because I'm probably going to be busy then, and I have to reset up the whole lab and everything, and that just takes so much time. Packing it all away already takes a lot of time, and I think rebuilding it will be even more effort. So probably no video in 2 weeks, but the one after that will probably be another project video, and then I'll probably have some time to dig some more into the old Tesla ICs. I've had a viewer send me some valuable documentation and all that sort of stuff, but I'm currently working through that. And but I think I'm going to have a new video on the transistor arrays by Tesla in about a month, I think. So yeah, hope you liked the video. Hope you enjoyed it, and I'd like to see you around on the next one.